Hi everyone, we are continuing Taylor series. So first we're going to start with just a couple of terms. So they're giving us a couple of terms and then the general term. They're asking us to find the sum, right? So I notice, yeah, this is what I'm looking for. I notice that we start with a constant, okay, and then we have factorials that are increasing in numeric order. So I'm going 1 factorial, 2 factorial, 3 factorial, and then the top is also increasing. It looks geometrically, right? And then I notice the same thing here. So I notice that this looks a lot like my e to the x. So I know that e to the x is the sum from 0 to infinity of x to the n over n factorial. Okay, and this one is 3 to the n over n factorial. So in this case, x is just equal to 3. Okay, so that means that the sum from 0 to infinity of, I'm going to write my general term here, is equal to e to the third power because x is equal to 3 in this case. Okay. Now, as we know, this converges for all values of x, so I don't really have to worry about where it converges. Okay, e cubed is going to converge in this. Okay. Next one. Here, what I'm looking for, again, I see that I'm alternating in sign, and my denominators are all odd factorials. They're all odd factorials, so I know that this is sine. Okay, I know that sine looks like the sum from 0 to infinity of, it alternates, I have x to the 2n plus 1. Hey, remember, that's a fancy way of saying odd in math. You might see that as 2n minus 1 in some papers or some books. But that only works if your index does not start at 0. Okay, you're going to have to start your index at 1. So we're going to write 2n plus 1 and then 2n plus 1 factorial on the bottom. Okay, and again, this is also convergent for all values of x. Anyway, so in this case, I see that x has been replaced by 2. Okay, x has been replaced by 2. So I know that this is sine of 2. So my sum, I'm going to write my general term here. Oops. Hey, this is going to be equal to sine of 2, right? So where x used to be, there is now a 2. All right, let's do another one. This one is just geometric. Now it's alternating, but it's also geometric. All right, so I'm going to treat this like a geometric series. I just need my absolute value of r to be less than 1. And if that's true, then my sum is equal to my first term divided by 1 minus my common ratio. Hey, well, I see that my common ratio is 2/3. Okay, the absolute value is 2/3, and so that's fine. So my sum is equal to my first term is 1 divided by 1 minus my common ratio, which is negative 2/3. Right? That's going to be 1 over 5/3, which is 3/5. Right, so the fact that it was alternating did not matter in this case. I'm still treating it like a geometric series. It's still totally fine. All right, so suppose that we're given some power series. Okay, I don't know what this constant is, and it converges if x is equal to -8, diverges if x equals +6, and then I want to see if these are definitely, maybe, or definitely not true. Okay, well, here's what I know. Right, just from looking at this, I can see that I'm centered at -3. Yeah, I know that because I have x plus 3 here. So I'm centered at x equals -3. It's like the opposite there. Or whatever you can plug in to get this term to be 0. Yeah, that's where I'm centered. Okay, I know that I converge at -8. So I'm going to draw like a number line. Okay, so I'm going to start at -3. Okay. I'm going to start at -3. Right, that's my center. And I know that at -8, I'm going to converge. Okay, that gives me a radius of convergence of 5. That means that if I go 5 in this direction to the left, I also will converge if I go 5 in the other direction to the right. So I'm also going to converge all the way up to 2. Now, what actually happens at the endpoints, remember, is kind of tricky. Okay, you have to test that, and in this case, we cannot test that because I don't know all of what's going on in my power series. But I do know my radius of convergence is 5. Okay, my interval of convergence, I'm not sure, but my radius is at least 5 here, and this is all definitely going to converge, any number between here. Okay, now I also know that if I start again at -3, up to 6, which gives me a radius of 9, I might converge. Okay, I know past 6, I definitely do not converge, including 6. Okay, past 6, including 6, I definitely do not converge. This didn't tell me anything about what happens between 2 and 6, though, right? So this gives me a radius of 9, which means that down to -12, I might converge. So between -8 and -12, I might converge. Between +2 and +6, I might converge. I don't actually know. So I'm going to compile all of that. I'm going to draw a better line than that. I'm going to compile all of that into one line. Okay, so I'm starting at -3, okay, up to 2 and -8. I'm pretty confident that I'm going to converge for all of these values here on the inside. Now again, at my endpoints, not 100% sure, but pretty confident I'm going to converge for all these values on the inside. Okay, then to -12 and 6, so between these values here, I'm not sure, I might converge. And then for every value outside of that, definitely do not converge. All right. So first they ask if I converge if x is equal to -10. Okay, well -10 is between -12 and -8, so I'm not sure about that. It might converge, so maybe. That's horrible. I'm gonna try that again. That's not much better, but all right, maybe. Okay, then it asks if I converge if x equals 1. Well, 1 falls between -8 and 2. That falls in my radius of convergence, so that's a definite. That's a definitely yes. Okay, converges if x equals 2. Well, remember, 2 is on the outskirts of my radius. I'm actually not sure because it's an endpoint, so that's a maybe. Okay, normally you would test those endpoints. Okay, then it asks if it diverges if x equals -9. Well, -9's out here. I'm not really sure what it does between -12 and -8. Okay, so this is also a maybe. Right, and then power series diverges if x equals -13. Yes, it definitely diverges because it's outside of my bounds here. It's definitely going to diverge. So that's a definitely. All right, let's move on. Okay, so we're given a theorem here, and this theorem talks about the derivative and the integral of a given power series. Okay, so here, the cool thing is that your radius of convergence will not change. The interval might. Okay, your endpoints, it may or may not converge regardless of what the original function does. Okay, but the radius will not change, and obviously where it's centered will not change either. Okay, so you'll be working with the same numbers, which makes things a lot easier. Okay, now notice what's going on here with the derivative. Hey, you've done this before, where you just take the derivative of each term. That's fine. Or integrate, you take the integral of each term. Okay, and that's fine. Notice what happens to the index, though. Okay, when you take the derivative, the index bumps up to 1, whereas here it stays at 0. Really, it could go down to -1, but this constant takes care of that. All right, so let's actually work through some examples. Now, we'll be using a little bit of this. All right, first they ask us to write the Maclaurin for 1 over 1 minus x. All right, well, this is geometric. This is geometric where my first term is 1 and r is x, and my common ratio is x. This is the sum of a geometric series. All right, so I can write this out as to infinity of x to the n power, okay, where x is my common ratio. All right, so the first several terms, not too bad, pretty straightforward, and my general term is x to the n. Okay, we already wrote that. Okay, now this is going to converge when my common ratio is less than 1. All right, so between -1 and 1, or I should say for values of x. So I'm going to write x here. All right, so when x is between -1 and 1, it will converge. Now, if you plug in these endpoints here to test them real quick, obviously it will not converge. If you plug 1 in, you get 1 plus 1 plus 1 plus 1 plus 1 to infinity. That's definitely not going to converge. If you plug -1, it oscillates. Okay, it goes like this, which will definitely not converge. All right, so I'm just going to leave it like this. Right, part B, they ask us to find the Maclaurin series for f prime. Right, so we can do that. You're just going to take the derivative. So my first term here, when you take the derivative, it goes to 0. But the derivative of the second term is 1, and then 2x, 3x squared, 4x cubed, and on until you get to your general term, which n. So you drop down your power, x, you subtract 1 from your exponent. So there's my general term. And now, again, and you can write this in your sum if you want. Remember, it starts at 1 this time because we took the derivative. And that helps out a lot because if you start at 0, then this thing kind of goes to a mess. You start with 0. Okay, so again, it's asking where I converge. Well, the same rules apply. Okay, remember your radius of convergence does not change. So I still need x to be between 1 and -1, right? And again, at this point, you would test your endpoints, and nothing changes there either for this case. Okay, it could change though. If you plug -1 in, you still get an oscillation. Okay, if you plug 1 in, you actually end up increasing. So 1 plus 2 plus 3 plus 4 plus 5 plus so on. That definitely diverges. All right, and then they ask us to find the actual sum of the series this time. Okay, well, we're going to use a little bit of what we already know. Okay, I know that f of x is 1 over 1 minus x. Right, so really we're finding the derivative. Okay, we're finding the derivative right now where x equals 1/3. So I'm going to take the derivative. Right, so if you take the derivative, you end up getting 1 over 1 minus x quantity squared. Right, so the negative from your exponent and this negative because of chain rule end up canceling out, so it stays positive. So be careful with that. And x at this point equals 1/3. Okay, we already established that. If you're having trouble seeing that right now, you could rewrite this as n times 1/3 to the n minus 1 power, right? So you can see that my common ratio is 1/3 right here, and that's what x is. So I'm trying to evaluate where x equals 1/3. Right, and so you end up getting 9/4, and that's actually the sum of my series. Right, that's how these relate. We're using the series to approximate 1 over 1 minus x. I wanted to know what the derivative was when x equals 1/3, so it's really asking the same question. It's just asking me to do this. So my sum is equal to 9/4. Okay, same question. Asking it in a different way, but it still is the same thing. Okay, now we're asked to do the same thing for an integral. Right, so this first question is actually the exact same as the previous one. Okay, so I'll just write it out again. I'm starting from 0 to infinity, x to the n power. Nothing too fancy here. And I converge between -1 and 1. And remember, we plugged those in already, and we found that both endpoints diverge. Right, now, if I'm trying to evaluate the integral, in my first term, the integral of 1 is x, and then x squared over 2, x cubed over 3, x to the 4th power over 4, and then my reverse power rule says I add 1 to my exponent, divide by my new exponent. So this is my new Maclaurin series for the integral of 1 over 1 minus x. Right, so you could write out your series here using your general term. Totally fine. Okay, and so again, I know that this is going to converge between -1 and 1, but again, we have to check our endpoints, and this is why it's important to check your endpoints, because if you plug -1 in to your series here, so if you plug -1 in, that's a -1. We end up getting essentially the alternating harmonic series. Okay, it's very similar to the alternating harmonic series, and I know that the alternating harmonic series converges. Okay, this is actually going to be smaller than the alternating harmonic series, and that converges. So I know that this also converges. So it does converge at -1. If you plug +1 in, you could probably guess what happens. If I plug +1, I end up getting the regular old harmonic series, essentially, which diverges. And so, or you compare it to the harmonic series, which diverges. So this still diverges, but at -1 it converges, which is why it's very important for you to check your endpoints always. Okay, so it converges between -1 and 1, including -1. Okay, and last one, they want us to find the sum of the infinite series. Again, they're asking us to evaluate the integral when x equals 1/3. Okay, so essentially, they're asking us to evaluate the integral from 0 to 1/3 of 1 over 1 minus x with respect to x. The reason why I'm starting at 0 is because that's where I'm centered. Okay, and then 1/3 is the value of x. Well, negative natural log of 1 minus x from 0 to 1/3. Okay, so the integral of 1 over 1 minus x is negative natural log of 1 minus x. Okay, we're going to plug in what we got here. So negative natural log of 2/3, it's going to be plus the natural log of 1, which is 0, so that goes away. And I'm going to simplify this just a little bit. Remember, if you have a number in front, a coefficient, you could bring that into your natural log as an exponent. So it'll be 2/3 to the -1 power, which flips it. So natural log of 3/2. The only reason I'm doing that is purely aesthetic. It just makes it look prettier, but that's it. Okay, this would be a fine answer as well. All right, that is it. I'll see you later.